Welcome all to the MfPH Next Generation Seminar Series and Networking event for early career scholars, junior modelists, and epidemiologists working on or interested in mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MfPH Next Generation est un événement pour les chercheurs en début de carrière, des modélisateurs juniors, des épidémiologistes travaillants ou intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Fields Institute operates for thousands of years. It has been a traditional land of Huron-Wendat, the Seneca, the Sogas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques, du Sogas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de tout Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today is Dr. Mortaza Baky. He is research associate at the Fields Institute for Research in Mathematical Science and also the Advanced Disaster Emergency Rapid Response Simulation and Lab for Industrial and Applied Mathematics at York University, where he explores the macroeconomics of the pandemics and post-COVID-19 environmental risk. He was an assistant professor at Haskuee and Tunis University of the Technology, Tehran, and a postdoctoral fellow at Bex University, Hungary, where he worked on computer general Behaviour modeling. Notre invité aujourd'hui, Dr. Mortaza Baky, il est chercheur associé au Fields Institute for Research and Mathematical Science et ainsi que Advanced Disaster Emergency and Rapid Response Simulation et laboratoire de mathématiques industrielles et appliquées de l'Université de York, où il explore la macroéconomie des pandémies, de situations post-risque environnemental COVID-19. Il était professeur adjoint à l'Université de technologie KN2C de Téhéran et chercheur postdoctoral à l'Université de Bex en Hongrie, où il a travaillé sur la modélisation de l'équilibre général. His talk today will be on containment policies, behavior and dynamics of the pandemic. La présentation aujourd'hui portera sur la politique de confinement, comportement et dynamique de la pandémie. Thank you very much, Doctor, for being again in our seminar series, and the floor is yours. Thank you very much.
Thank you, Idris, for introduction, and thank you for organization. And I would thank all organizers. The topic that today I'm interested to share with our audience is the containment policies, behavior, and dynamics of pandemic. Before I start the presentation, I would thank Professor Kumar Murthy, the director of the Fields Institute for Research in Mathematical Science, for his support and contribution as well, and Professor Masoud Efendiev, a visiting scholar at Fields Institute. During the time that he was here, he contributed in this research, and we submitted the paper jointly. Okay, so the topic that we will talk is an interesting for myself, first of all, and I hope that is interesting for other people, because during the 3 years of the pandemic, there are too many research projects and papers considering the dynamics of the pandemic from different point of views. And this research aims that to contribute to the literature and extend the literature. We will start with a short introduction, and we will state the problem, and then we will go to a more general framework that this research applied to analyze the interaction between containment policies and people response or behavior of people with respect to these policies, and then the outcome of the outbreak. And also we will talk about the transmission dynamics which is a more generalized SIR model derived from this behavioral epidemiological framework, and then we will discuss our result at the end. As you know, since the time of the outbreak, the COVID-19, mathematicians and also epidemiologists use the SIR model and its variations to predict the disease transmissions. And these models are powerful tools to analyze the mechanism and dynamics of the outbreak. But like other methodologies and other methods, there are shortcomings. The main assumption behind of these models is that the people contact each other randomly. So like the particles of a perfect gas within a box. So the rules that governs the behavior of the gases are assumed to be applied to analyze the behavior of the disease between the people and their contacts. So it means that the same rule, which is so-called law of mass action, is applied to analyze in fact, the interaction and the contact between people and the transmission of disease. So based on this approach, in fact, ignores the role of behavior of individuals and also the government policies and their effect on the outcome of the pandemic. We know that the government, all governments around the world use different measures to control the speed of the outbreak. And the investigation shows that most of these tools have been effective and significant to reduce the number of infection, and also this through the reduction in the number of contacts, because these tools mostly impose restriction on the contact between the people. For example, the closure of the workplaces, schools, and gatherings. These tools and measures restrict the number of contact, and finally could be effective in reduction of the number of infections over the period of the disease. But we know that the people response to the policies and to pandemic is different. People with different attitude to the risk respond differently to the policies and also to the pandemic. So we should have a more comprehensive framework to analyze the behavior of the people. In fact, the questions that we are going to answer in this research is that how the interaction between the containment policies and people responses can affect the effectiveness of these policies, and ultimately how can affect the outbreak outcome. Okay, as a minor question, we will talk about the mechanism that the government decides on these measures to control, how the government decides to design and how to design and implement the policies to control the disease. And also we will talk about in this research we investigated and we answered this question, that how the people decide to respond to these policies. The framework that we use is the behavioral epidemiology, and this is the approach, general approach, that we integrated the behavior of agents into the SIR or SIR family models. So this approach explains the effect of the individual's response during the outbreak. And as you know, that there are too many papers, research projects in epidemiological modeling, that these studies assume that the contact rate between individuals are not constant, and the contact rates is decreasing, and is a function of the number of the infections and the disease prevalence. And also they assume that the force of infection in the model is non-linear, and you can find in the references that I mentioned. And also some paper integrated the impact of the behavior of these agents on the contact rate. And also this paper argued that the information that people use not only change their behavior, but also affect others people behavior. So like the game between the people, and some game theoretic approach are used to analyze this the behavior of the people in response to others. So it means that when the people, for example, act, the other people react to their act, okay? And then this reaction to their action will affect the dynamics of the disease. Regarding the containment policies, you know that evidences show that the complete and effective implementation of the non-pharmaceutical interventions have been effective to reduce the number of infections. There are too many researchers that show the positive impact of the policies on the number of infection. And also the policies that the government set and targeted to reduce the number of infection has decreased the number of the contacts over the period of the crisis. For example, in United States of America, there are too many studies show that the public health policies reduce social contacts and consequently the number of infection during the first wave of the COVID-19 outbreak. In the case of China, also there are some researchers, I mentioned two major one here, that the restrictive measures by the government have been effective to reduce the number of infections. For our model, as I mentioned, we assume that the policies, the public health policies that mainly we call them containment policies, designed and conducted based on the level of the information that the government receives from the level of the outbreak. In other words, the containment policies are fine-tuned based on the information set that the government have regarding the level of the outbreak. It means that the government utilize this set of information to optimize a utility function or minimize a cost function that we will discuss here. So, and derives the optimal path of the policies, which is a set and a combination of different tools that we will discuss in following slides. So, and also we assume that the individual also decide to comply with the policies using this information, okay? And this information forms their perception of the risk. The perception of the risk is a main factor in their decision. And also the people use a cost-benefit analysis framework to analyze the costs and benefits of different behavioral attitudes toward the disease. So they will compare the cost and benefit, and if there is the costs are more than benefit, they will change their behavior that we will talk later. So The other component that we discussed and I talked about that is the information set. In this model, information and changing the information is a component of our model. So we integrated the information set into the model, like not only in the decision by the government and the people, but also as a compartment, as a main component, not compartment, the main component in our model, that we will see how the information changes over time, and we will derive the mechanism of the change in the information set. And then based on the change in the information, we can derive the change in the behavior of the government and the individuals. So a conceptual framework that we use to analyze this problem is here. As you see, here the M is our set of information, and Z is the set of the policies, or which is an index we will talk about. And also B is the behavioral variable with respect to the pandemic and response of the people to the policies. And IT is the outcome of the outbreak in terms of the number of infected people. So as you see, there is a causal relation. It means that not only the information set affects the government behavior, but also affects directly the behavior of the people. People respond in response to the government policies, and government policies also will be adjusted in response to the behavior of the people. And this behavior from the government side and the people's side will affect the information. So the information changing over time. So, and then this set will affect the number of infections. And there is also a causal from that side to the behavior and the set of information. So the system is dynamic, and it's a dynamic system that shows the interaction between all components. The first step is to explain the set of information and the formation of the information. We assume that government and people use this information in their decision. For this, we assume this integration for the information set. But we assume that the information follows this form, which H is a function of I. I is the number of infections. So here we assume that H is an increasing function, and K of tau is a kernel function. That this kernel, for this research, we assumed a 2-scale kernel, which reads as follows. So in our kernel, we have two T, T1 and T2. T1 belongs to the time that the information is formed and acquiesced by individuals and the government. T2 belongs to the fading of the memory. By the fading of memory, I mean that when there is a news, there is an information released or data released by the authorities, people respond to and take that information into the decision making. But over time, the weight of this information will decrease. So there, because of that, we assume the fading of the memory, like the other in financial markets. Also, the modelers and mathematical modelers use such a assumption. So H is an increasing. We assume that is increasing because for the positivity of the model, we need to assume that H is increasing. And also under the exponentiality fading memory, we can solve and we can find that M is and will be reduced into differential equations. And based on that, we can have two M prime one, which is the change in information with respect to the time of information acquisition and formation, and M prime 2 is belongs to and related to the time the fading memory. So we have these two set of ordinary differential equations, and these equations in fact shows the dynamics of information formation and acquisition, as well as fading of the memory over time. So in the case of the government, and to analyze how the government decides on the set of the tools or measures to control the disease, we assume that the government use a continuous Markov decision process. And this form will be explained here. We assume we have a space of X, and with its sigma algebra, that will be a continuous time Markov decision process as 5 tuple defined as follow. So here S is n-dimensional continuous state space, which is a set of states of our system. Our system is in fact based on the number of the infectious recovered and all the compartment in the compartment models. So in the case of A, A is in fact the action space. The government has a set of actions, can decide on them, and a combination of them as well. In each state, the government set a combination of these measures to control the disease. And to decide, the government, in fact, use the set of information with a targeted level of the information. As you know, the level of the information is an index of the level of the disease outbreak. So M depends on the number of infections. So the government can target that index. And then if the information is above that level, then the government will conduct the policy. And if the information index is less than the index, the targeted index, the government will release that action. For example, in terms of the workplace closure or openness, the government can decide to order the businesses to close or to open, depending on the level of the M. If it is higher than the M star, then the government will force the businesses to close. Okay, so the transmission probability is another part of this our state space, which is here. We can assume for any policy pi, we have a minimum transition function, which the probability follows the following integration. And there is a cost for any action. So any action by the government has a cost. So the government should minimize the cost. So we should define the cost function. Here, the cost function is a measurable real value function, which defined in terms of the action in each state. So the cost of any policy is defined here. And also for any discount factor, we can have the expected discount cost function. An optimal level of discount cost function can be defined as follow. And the government can solve this optimal problem in this dynamic programming problem and use the dynamic programming techniques. For example, the government can use the Bellman equation for this continuous time MDP problem. So the next step is to explain the behavior of the people. How do the people decide? As I explained, the people decide based on the same set of information that forms their perception of the risk. And also they compare the cost and benefits of different attitude or approaches to the compliance to the policies. So based on this, we can have two level or two group of the people responses. The first is natural response, and the second is imitation response. The imitation response takes the behavior of other people into account, and people decide based on the behavior of others and make a cost-benefit analysis. And natural response is their natural response regardless of what other people are doing. So as I said, the risk perception is the driving factor, and the people use the cost-benefit analysis to decide. Based on this, we can have two levels of compliance. So the people can switch between two levels of the compliance. And we know that the low level of compliance has less economic cost, but more risk of infection. The high level of compliance has less level of risk of infection, but has more cost in terms of the, for example, reduction in the income that people receive when they close their business, or for example, they limit their activities, so their income will decrease or their utility will decrease. Here, we assume that all these economic factors can be translated into the utility function. So any change between two levels of this compliance depends on the magnitude of the risk perception and the way that they give to the cost and benefits of any of them. So people choose between this level of the compliance. So a low level, as I explained, indicates a minimum compliance based on their perception of risk, and the high level of compliance is chosen by those people that weigh the infection risk, because the infection risk is more important for them. Okay, they perceive that they will be highly exposed to the infection risk. So, and the natural part, as I explained, that the natural part is regardless of the other's behavior, they respond by themselves to reduce and to make themselves safe. So to be more safe, they respond and they, for example, follow the rules, they wear the mask, they restrict their contact with others, regardless of the behavior of the other people. So for both level of this compliance, we can assume a payoff or the benefits. So the payoff for both level will be PL and PH, which depends first on the level of the information that the people receive, and also depends on the policies that the government implements. Here, ML and MH are the sensitivity to the information that the people receive. Since we assume that the information changes over time, here we assume that the elasticity to the information that the people receive is constant for each groups. But on the other side, we assume that the set of policies will change based on the mechanism that we explain. So As I explained, the higher level of compliance has more cost because the people will lose their income, they will lose their ultimately their utility because of less contact with other people. So the fading memory mechanism that we explained before is important part in our model as well, because this the information that the people receive will be adjusted, will be modified, okay, over time. So we assume the fading memory mechanism for our model. So this mechanism modifies the perception of the risk. So over time, the people will be less respective and responsive to the previous information that they have received. So they respond more to the new or recent information or news that they will get. So, and the perceived prevalence of infection is influenced by recent information. And the past information gradually decrease, its roles will decrease in the decision making. And finally, the change in the level of compliance in population derived with respect to the modification of this perception of the risk and how they perceive this risk. Okay, so and as I mentioned, that the cost is higher for those people that highly compile to the policies. And okay, I just explained this. And here I want to explain how the people switch between two levels of compliance. Suppose that we have delta P, which is the difference between the payoffs for the low and high level of compliance. And here, based on the sign of delta P, the people will decide to switch between two levels of the compliance. Here we assume that the people sample others, or individuals sample other people's, they witness the other's behavior, and then they, based on that, they switch, the individual change their behavior into high compliance with the probability of gamma B multiplied by B. The gamma B is, in fact, a factor, is between 0 and 1. And B is the full compliance. So the less, it means that the low compliance is 1 minus B. So here, if the low compliance is higher than the high compliance, then the change in the behavior is derived by this function. In the case that the higher level of compliance is more paid, or its payoff is higher, then the deriving function is as follow. Number 16 shows that here the people will switch when the payoff is much higher in high compliance. Okay, so, and we can combine them to derive the average change between two, or the total, in fact, the switch between two situations. Here, dB is the combine between two situations, two level of the compliance. And we talk about the natural response to public health policies as well. Here we assume that Q is the probability of reduction in the probability of reduction of the infection rate. Here there is a mistake in presentation, sorry. It should be the probability of reduction in the probability of infection. I should say the rate of infection. It means that if people, for example, follow the policies, how much will the probability of infection will decrease. Okay, so based on this, we can show that the change in the behavior regarding this, the probability of the infection or the risk of infection, the behavior is derived by this function, which BT, as I explained, is the behavior of the people in the highest level, and 1 minus is in fact the lowest level, and Q is the probability of infection, and I here is the number of infection, and S is the number of the susceptible, and Z is the index of the government policy, and theta is the infection rate that we will discuss later, why we assume that it's a time varying theta in our model. So if we combine the natural and imitation part, the behavior of the individuals will be governed by this function that we combine. In this combination, we weighted two, natural and imitation, equally. But another approach can weigh differently, and the results will be completely different if we weigh, for example, natural response to public health policies more than the imitation, or we weigh the imitation more than the natural. But here we assume that they are equally add up. So this is the function that we will use in our system of equations. So based on the previous discussion, our behavioral augmented SIR model is as follows. The first equation shows that the change in the number of susceptible depends on the behavior of the people, the policies, and the perception, the probability of the probability of reduction in the risk of infection. And the second equation derived based on the first equation. And number 22 is the mechanism of the change in the government policies. As I explained, it depends on the level of the information that the government receives. And the equation 24 explains the change in the information. And the change in the behavior, number 23, here explains the change in the behavior of the individuals. As I explained, depends on the level of the policies, the probability of reduction in the risk of infection, the information that the people receive. Okay, so finally, the number 24 explains the mechanism of the change in the information based on our causal framework. You see here that the change in the information set depends on the number of infection, as well as the policy and the previous the level of information. Sorry. Okay. This is the system that we solved to analyze the mechanism of the outbreak. So here I explain the main parameters. We talk about the Q, but here we will talk about theta. Theta is the time-dependent rate of transmission that we assume that depends on the average social contact number, as well the probability of contact to an infected object and the probability of the virus transmission. So theta t is a function of these components. Here, CT is average, that we can calculate the average based on the distribution of the population, and it's also time variant, but two other components are constant, and we have taken them from the literature. So here, the number of contacts, we assume that the number of contacts is updated by the following mechanism, that it shows that the level of the contact, average level of contact at each time, depends on initial number of contacts, which is the number of contacts before the pandemic, the level of the policies by the government. Here, Z bar is the maximum level of policy, and Z0 is the initial level of the policy by the government. And RZ is the change in the rate of the policies that we will talk how we derive this rate, and also the maximum level of the compliance or the behavior of the households, and also the initial, and also the change in this the behavior of the people. So here to calibrate this updating function, in fact, we need to estimate some parameters, especially RZ and RV should be estimated. To calibrate transmission rate, we applied an updating algorithm that we explained to calculate the contact rates. Okay, so for that we used a social contact matrix that is in the reference, and we aggregated this contact matrix into average. The initial contact matrix that we used was designed for different settings, for the household, school, workplace, and the last one should be for the community. Sorry, that's wrong. I'm so sorry for this notation. So here the number of contacts for different age groups are used, and we aggregated them into the total number of contacts for each age group. And then we applied the average for the initial, and also we updated the number of contacts based on the function number 27. So for the government policy, we use an index, Oxford COVID-19 Government Response Tracker. This index is a database, in fact, that collects the systematic information of the government response to the pandemic. They have different components based on different, in fact, measures, from the school closure, workplace closure, gathering, public activities, transportation, and international activities. These are measures that are reported and then weighted, and the weighted average is between 0 to 100. And we normalized this index to estimate our model parameters. So to estimate the rate of decrease in the policies, we use a scattergram of the index in front of the cumulative number of the cases, and we use a kernel regression and fitted this kernel regression to our data to estimate our parameters that we applied to calibrate our model at the last moment. Okay, this kernel shows the cumulative versus the OXCGRT. Here, as you see, the index is between 0 and 100. The maximum level for the Ontario province was less than 80. And as you see, it starts from at the initial point, the government was observing and was just developing some instructions, and then there was an increase, a sharp increase in the level of the policies, and then, as you see, with the number of cumulative, there is change in the level of the policies. So we simulated the model first for generally for initial values and initial parameters, and then we simulated for the different parameter values. This is the result for our initial model that compares the result for two cases, two scenarios, with and without the policies. Generally speaking, the policies have been effective, and our model also shows that the policies decrease not only the level of infection, the maximum level of infection, also the peak of the infection has been postponed. So it means that if there was no policy, we should have more level of the infection. So we also simulated the model for different level of informations. As you see, when the level of the information changes, the number of infection changes, the mechanism of infection changes. And here we observe that with increasing the level of initial information, there is a change in the number of infection. And the behavior is different. The behavior here depends on the perception of the risk. As I explained, there are two components when the people receive the information, and the other is the fading memory that we discussed. So the difference between the shades of the number of infection under different scenarios depends on the behavior of the government and the behavior of the people. So this is, in fact, the result of the interaction between all factors that we integrated in our model. So we also simulated model for the gamma, in fact, the probability of the changing in the imitation behavior, or as we discussed, the gamma is the response of the people when they sample other people and then they switch to another, in fact, level of the compliance. So gamma B also is effective, and the behavior of the number of infection changes with respect to change in the gamma, as well as you see here, not only changes the change in the gamma not only changes the level of infection, also the mechanism of the change over time. So the last parameter that we simulated is the probability of reduction in the infection when the people follow the policies. So here we simulated for model for different values of Q. As you see here, the model shows that when there is higher level of the higher level of the reduction in the probability increases, then the people will be less conservative. They will follow less, or they will switch to the low level of compliance. And this is in fact this is consistent with the psychological approach of the people and perception of the risk. Okay, so in conclusion, our study highlights the complex interaction between containment policies, public risk perception, and behavior change during the pandemic. And our result emphasizes the need for a dynamic policy adjustment mechanism. It means that the government should adjust its set of policies with respect to the new information and the response of the people. And also here, sorry, the last one was the insight on the targeted and adaptive public health that the government and policymaker can use the result of such a research. And yeah, that's it. And here are some resources, and I at the end, again, I appreciate the support by Professor Kumar Murthy and also Professor Masood for his contribution. And I declare that this project was financed by Mathematics for Public Health program. Thank you, and I'm waiting for questions and comments.